Yeah. So first, um, I'm going to, so in this lecture, I'm going to try to describe formalism that we recently developed. It's the co-adjoint orbit method of bosonizing the Fermi surface. I must first warn you that it is not, is still not the standard way that you would find in textbook or in review. There are, if you need to read about a standard approach to Fermi liquid, then there are a few references that I can recommend. First, if you can read long text, then the first 200 pages of Abrikosov, Gorkov, Zelashinsky is something that I would recommend everyone to read. If you want a very short text that capture very essential idea of the more modern way of thinking about the Fermi liquid, then you should read Polchinski's Tassi lecture of 1992. Okay, so last time we have discussed the, we have talked about the difficulties of understanding Fermi liquid as a quantum field theory. Basically, if we follow Landau's kinetic equations, starting from an initial state, which can be thought of as a field Fermi surface, when F is equal to 1 inside, F equals 0 outside, subjecting the system to external electromagnetic field, we will find some intermediates, a state at intermediate time to be represented, roughly speaking, by this picture, where the Fermi surface is distorted. It remains sharp because we follow the Liouville's equation. F equal to 1 inside, F equals 0 outside. And here is the picture in momentum space in a given slide of space in time. So this shape of the curve is also a function of t and x. We know the equation that governs the evolution of this shape. That equation is given by Landau. Today we want to reformulate this equation as an equation of motion coming out from an action principle. So I'm going to jump to one object that we will need. Here is the object called the group and the algebra. First, the algebra of canonical transformation. And this seems to be unrelated to the problem at hand, but you will see at the end that it's a very useful thing to talk about. So let's consider classical mechanics of a particle in phase space. The phase space of the particle has 2D coordinates. D is the number of spatial dimension. And in classical mechanics, we know that we can describe the evolution of the system by the Hamiltonian equation. So let me write like this: C dot equal the commutator or the Poisson bracket of C and H. With by C, I mean either the coordinates and momentum. Okay, so the Hamiltonian is a function of x and p. In fact, we can talk about the evolution of any function of x and p. If I have f as a function of x and p, f dot would be still equal to the Poisson brackets of h and f and h. And the Poisson brackets, let me write it once to fix the notations. F over p minus d h over x. This is one of the rare occasions where I do not follow the Landau-Lifshitz convention of sign. Okay, so now the Liouville equation. In the Liouville equation, we talk about the distribution functions that of particle in phase space. Rho is a function of p and x. Okay, and if you look at the Liouville equation, it has the following form. It can be written as rho dot equal to h rho. Okay, and here it's the equation just has the opposite sign compared to the equation on the left-hand side. So what you can recognize here actually is the classical analogs of evolution equation for the operator in the Heisenberg formalism in quantum mechanics, and the equations of evolution of the density matrix in quantum mechanics. They have roughly the same form, except the Poisson bracket is replaced by the commutator. Okay. Now, the Poisson brackets define an algebra that is the algebra of canonical transformation. The algebra is defined in the following way. Any functions of x and p, let me call it f. Any function of x and p correspond to a generator of the algebra. So the algebra is infinite dimensional. The functions f of x and p can be thought of as a expansion, as the coefficient in the expansion of this generator in certain basis. And the algebra is given by the Poisson bracket. So if I have the commutator of these two generators is going to be another generator given by the function that is the Poisson bracket of f and g. Okay. One can think about generator of canonical, what a generator of this algebra as something that gives an infinitesimal coordinate transformation in phase space. So a generator f can be thought of as something that does the following operation: x goes to x plus epsilon df over dt, dp, and p goes to p minus epsilon df over dp, dx. Sorry. Okay. This infinitesimal transformation preserves the Poisson bracket, and so it is a canonical transformation. Two of these transformations commute to another canonical transformation given by the Poisson bracket of the two functions. Now the group, one can exponentiate the elements of the algebra to give a group. So the group are, roughly speaking, given by exponents of these generators, e to the power of f, where f is a member of the algebra, and this does the following transformation. If I act that on the function g, it will map g into g plus f of g plus 1/2. Sorry, let me write the Poisson bracket. F g plus Taylor series. Actually, I'm mixing up the mathematical terminology. Here, what I'm writing is a representation of the group of canonical transformation called the adjoint representation. But one can also think about this as from the physicist point of view, one can think about that as the definition of the group, as the group of finite canonical transformation. What I'm writing here is just this kind of transformation, but exponentiated. Right? So yes, the algebra can be thought of as infinitesimal canonical transformation. An element of the group give us the finite time evolution under this evolution in unit time. You can actually think about this as just Hamiltonian evolution, with F playing the role of the Hamiltonian. Okay, so that's, I've defined the group. And now I'm going to define at this moment. So this actually is the what in mathematics called the adjoint representation. At this moment, if I was a mathematician, I would define for you what is the co-adjoint representation. But because we don't have a lot of time, I'm going to skip that. And I'm going to apply right away this to our problem. So here we are dealing with a system of fermions where we want to compute expectation value of various operators. So if you have a fermionic state, right, with the, say, distribution function equal to f as a function x and p, and say I want to compute the total momentum of our system. The total momentum p of the system is equal to integral over dp dx over 2 pi d times the momentum of each particle p and the distribution function f of x and p. So integrating out over p, I get the momentum density at the point x, and then I integrate over x, I have the total momentum of the system. Okay, so here I'm going to do the following. I'm going to interpret that p here as an element of the Lie algebra. So it's a generator of canonical transformation, of the algebra of canonical transformation. Any function of x and p is a generator, including this. Yeah? And here, for simplicity, it's not really what I should do. If I was a mathematician, I'm going to consider this also as a generator, as another generator of the canonical transformation. And write this as the scalar product of two generators. One generator is this f, and the other generator is this function p. Here I have done the following. I have defined in the Lie algebra the scalar product. Scalar products of two generators is simply integral over phase space of f of x p and g x and p. And one can check that this scalar product is invariant under canonical transformation. So if I do this canonical transformation, which I will write using a slightly sloppy language as e to the f g e to minus f, right? Then I can show that this is equal to, say, e to h f e to minus h e to h g e to minus h, when the transformation laws are given by this this series on this board. I would, if you had a little time, it's very easy exercise to prove this fact. So here, what we are going to do is to have the following interpretation of our system. So let me draw a board. Then so if I have a physical observable, a physical observable is going to be put into correspondence to a function of x and p, which is elements f, elements of the algebra, of the Lie algebra of canonical transformations. In fact, here we are limiting ourselves to one particle, single particle observable, like things that can be written as sum over the properties of a single particle, like this total momentum, sum over momentum of all particles. Okay, now the state of the system would be, I would put it in correspondence with another function of f, of x and p, let me call f, small f. Well, here I'm going to consider as a element of the Lie algebra. More rigorously, it should be considered as the elements of the dual space. And the expectation value of the f in the state characterized by the distribution function f is going to be equated to the scalar product of small f is big F. And here I'm going to draw for you quantum mechanics analogs. A physical observable is an operator in quantum mechanics. Here we are dealing with operator that can be written as some function of x and p. Say it can be expanded in as a polynomial in x and p. A state is given by a density matrix rho. So in quantum mechanics, it's still a symmetric Hermitian matrix. So one can interpret that as an operator in the Lie algebra. And this one is just trace of rho and f. Okay, so now I'm going to define what the co-adjoint orbit is. Okay, so let's take a given distribution function. Say the distribution function of a Fermi gas at 0 temperature in the ground state. F0. I call that F0. It's a function that is theta function of Pf minus absolute value of P. So it's equal to 1 here and 0 outside. Okay. Then I'm going to apply various canonical transformation on that function. So I will get f equal to e to the phi f0 e minus phi, which, as we said, is equal to simply f0 plus phi f0 plus 1/2 of phi phi f0 plus dot dot dot. Or so if f phi is a function of X and P. One can think about this as the following, doing the following exercise. We take a system of fermion, and then we say that there is a Hamiltonian, a single particle Hamiltonian. Each particle moves according to this Hamiltonian phi in unit time. And then we follow the evolution, right? And the final distribution function is going to be given by this formula. And the result will be some kind of new Fermi surface, which can be not round, it can vary in space. So that is the new state of the fermionic system. And it's one can show that one can get to any shape, at least in the vicinity of the round surface, we can reach any point, given that this point has the same number of particles as the original state. Okay, so this can be used now as a convenient parameterization of the Fermi surface, at least. Previously, we have this problem that we have a Fermi surface, and there is not a very good way to parameterize deviation of the Fermi surface from the round shape. We could do various parameterization, like the height function, etc., but none of them have the same generality as this parameterization. Yeah. The total particle number is conserved. You can see it by doing the following. You integrate this over phase space. You can show that integral of a Poisson bracket is 0 over, but you have to integrate over the whole phase space to show that. And all the other terms are Poisson bracket, so they integrate to 0. Okay, any question? Any function of x. It's any function of x and p. Yeah, it's a phi there. So what is the equivalent things that we, what is the finite dimensional equivalence of this co-adjoint orbit? We can, instead of the group of canonical transformation, we can think about spin, for example, in SU2. So we can take a generator, which is some vector n, which is n1, tau 1, n2, tau 2, n3, tau 3, where tau 2, 1, tau 1, tau 2, tau 3 as the 3 generator of the SU3 group. We rotate it using any element of the SU2 algebra, and you find that you reach a sphere, right? A sphere. And so this co-adjoint orbit is not the whole space, whole linear space of all these functions. Only some function is reached by this procedure. In our case, this function always have the properties that it has a sharp Fermi surface, 1 or 0. Also has the properties that the total number of particles is the same as before. Another feature that we see here is that this parameterization of a Fermi surface in terms of the function of x and p there is a redundancy. That many functions of phi can correspond to the same shape. Namely, if we have some elements of the groups, let me call that e to the power of alpha, so that e to the power of alpha times f0, e to tau minus alpha is f0, then e to the phi and e to the phi times e to the alpha would correspond to the same shape of the Fermi surface, because applying e to the alpha to f0 doesn't do anything. So you apply both, we get the same shape. So the co-adjoint orbit is a coset of the group of canonical transformation. Let me call that G divided by some H, where H is the subgroup which preserved the original Fermi surface.
It's clear that the first will stay sharp, like it's at 0 and then you go back. Is it clear that it will still be
Sharp?
Yeah,
because it's a Liouville evolution with f with phi being the Hamiltonian, and so the surface remains sharp. So let's actually convince ourselves by explicit calculation that the surface remains sharp. Suppose I have a function of phi, and then I compute. Let's assume phi to be small, so that we can limit ourselves in this series f0 plus phi f 0 to only the first term. F0 is theta function of p f minus p. Okay, this one is the Poisson bracket, a Poisson bracket of phi with the theta function. You have to differentiate the theta function over p f0 and then the phi over dx. So differentiating theta function, you get a delta function of pf minus p, but up to a sign that I'm not following, times the direction of p, the gradient of phi. Okay. It looks like we do not get a theta function, but actually this can be thought of as a expansion, linear expansion of the following theta function, pf plus p hat grad phi minus absolute value of p. P hat is the direction of p, vector pointing in the direction of p. Okay, so plus dot 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 term of second order in delta in phi, which we ignore. And so again, here we have a Fermi surface, which remains sharp, and the deviation from the original Fermi surface is given by this function, p times grad. The deviation here is p times grad of phi. And this is, for small phi, it's actually evaluated at point x, and momentum equal pf times p, right? Because all we need to know is the behavior of this function near the Fermi surface. Okay.
Volume the same at all x.
Sorry?
The volume is close to the same at all x.
Volume is different x. The volume is, you have to take the integral of this over p. And since this is could be a non-trivial function of p, it generically you have the variation in density. In this calculation, you also see this statement of ambiguity, of redundancy in the parameterization. The shift of the Fermi surface depends on the gradient of the function phi along this momentum direction, but only depends on the gradient of phi at p equal pf. But when the absolute value of p is equal pf, it doesn't matter what the canonical transformation does for particle deep inside the Fermi surface. So the canonical transformation is a shift, a position of different particles in different direction. But what happened inside here is almost has no matter, no importance. And so if one parameterize this group of the stabilizer group of F0 and then work out what is the redundancy, one can show that it's possible to fix the gauge in which phi is equal a function of Tx and only the position on the sphere, on the Fermi surface. So the dependence of phi on the radial direction can be arbitrary. One can put it to be absolute value of p to any power we want, say 0. Let me put at 0 power, but one can put it at, say, first power. It just corresponds to working in a different gauge. The radial dependence of phi is completely something one can fix by choosing a gauge.
F is basically the single particle density matrix, right? So that you would expect that the time evolution of that would be determined by some Hamiltonian. So the stabilizer that you, the gauge redundancy that you mentioned, so wouldn't you have to make sure that that also commutes with the Hamiltonian? Or
the stabilizer, I'm not talking yet about any Hamiltonian yet. I'm just parameterizing different shape of the Fermi surface right now, right? So it's no, yeah. Generically, it's not would not commute with the Hamiltonian. But this is a way one can see, for example, that in the effective field theory description, there will be an infinite number of scalar fields, each one field per point on the Fermi surface. Right? These are just the parameter that parameterizes the co-adjoint orbit. Any question until now? Yeah.
How special is the fact the symplectic structure that we have here is like EX the usual structure. That was modified it and it would say the symplectic structure would be EX. Would anything change?
Well, you have to rework all this construction.
But nothing fundamental.
Yeah, the whole formalism that I'm going to describe are just can be transferred with the modification.
Does this fully fix the gauge?
This doesn't fix completely gauge. There is a residual gauge transformation that one can also work out. There is a smaller group of residual gauge transformation that keep this form invariant.
What would it totally gauge fix by?
I'm not sure. Yeah, I don't know if there is a natural way to natural gauge condition that would completely fix the gauge. Here's I can think about this ansatz on the dependence of phi as a function of absolute value of p as a gauge condition, and then fix the gauge this way. But it doesn't completely fix. Yeah, so I think this might be actually useful at the end, that this residual gauge transformation is something that forbids various terms that one can write down.
Totally gauge fixed by even dependent there?
It will. Yeah, this is not negotiable. Yeah, the fact that there is an infinite number of fields we need infinite number of fields to parameterize shape of the Fermi surface is just physically, yeah.
You're starting from a theory that only has a finite number of fields.
The starting theory is that, but then when we go to the infrared, let's go into the infrared, we face the situation that we have a Fermi surface, and the specific heat of the fermionic system is linear in T, which is much larger than specific heat of any, say, conformal field theory. So here you see T is much larger than T cubed, or T to the fourth, at small t. So we need to have an infinite number of scalar fields to encode this fact.
Why is the gauge theory independent of the moment? So what is the shape of the Fermi surface? Is it banana?
Is what?
Is a banana, so that single angle cannot fix the gauge.
Well, here, in principle, here's the gauge fixing condition that I'm well, here I'm going to limit myself to small perturbation near the Fermi surface. But the formalism, the formula that I write down can be applied to any shape of the Fermi surface, given that it has the same topology as the original Fermi surface. But one need to fix a different gauge condition then.
Sort of like a boson. Just following this analogy, add and draw, then it somehow looks like you're parameterizing sort of like an equivalent ground space.
So it's probably easier to think about 1 + 1 dimension in this case. So in 1 + 1 dimension, the Fermi surface becomes 2 points, and you have 2 bosons on each of the points, right? So this can be, you can think about that as the scalar field that parameterizes the position of the Fermi energy on the left, on the right. These are not really Goldstone boson in the sense that there is no, it's not a, well, let's say, you can think about this way. In higher dimension, this will not be, this canonical transformation is not going to be a symmetry of the Hamiltonian. Hamiltonian doesn't have that many, there is an infinite number of symmetry here, but the Hamiltonian has only a finite number of symmetry. So one cannot think about this phi as a canonical Nambu-Goldstone boson that comes out from spontaneous breaking of symmetries, because then you would have only a finite number of these. Okay, so this is the parameterization of the Fermi surface, and now we want to write down I want to write down the theory that encodes the dynamics of the Fermi surface. Okay, so what Landau did for us was to say we have to think about the Hamiltonian, and we know the Hamiltonian of Fermi liquid. So I'm going to just say that the Hamiltonian, so let me draw some kind of a picture here. So we have we can think about this co-adjoint orbit as some kind of a infinite dimensional space. Each point in the co-adjoint orbit corresponds to a given distribution function f that's obtained from f0 by a canonical transformation, a sharp Fermi surface has. Landau tells us at least that we have a Hamiltonian as a function of f, right? And it can be written in expansion like this. So it's function of f. The first term can be thought of as the expectation value of the single particle energy in the space with distribution function f. The Landau parameter have to be written in expansion. So like dp prime dx, some function, Landau function of p in p prime, delta f p delta f p prime, etc. But it is just some function that map a point on the co-adjoint orbit to a number. Right? So each f becomes has an energy. Okay, so now we know that the Lagrangian, the action of the system will contains the following term: minus integral over dt Hamiltonian of f. Now f can be a function of time. Okay, but we need to have another input that is this previous lecture. We call that the Berry phase term in the action. Right? That the Berry phase term that has first derivative in f, so that the variation varying this action, we get the equation of motion. Okay, so now I'm going to write it down. I'm now going to write these things down. So for simplicity, I call this u f0 u minus 1. So f equal u f0 u minus 1. And I can write this term, I can write this term in the following way. dt, yes, I'm going to give two different expression, u minus 1 dt u, or equivalently, I can write it in the Wess-Zumino way, dt ds, introduce an extra coordinate, and then this would be f u dt u minus 1 u ds u minus 1 commutator, and then expectation value. Okay, it's two different forms of that. Usually, if one has Wess-Zumino Witten term, it is not normally possible to rewrite it in a form that is free of the extra coordinate. But in this case, one can do that with the price to pay, and the price is that this term, this Lagrangian density is not invariant under u goes to u times h, where h is in the stabilizer group, but is invariant only up to a total time derivative. And so, yeah.
F.
This one is F0, if I'm not mistaken.
And what about below?
Those. And you see this order of u in u minus 1 has reversed. Yeah. Let me check one more time, make sure I get this right. Oh. U minus 1 u. Okay. So the properties of this action is the following. It's the most important thing to check is that it is not dependent. The action is not dependent on the parameterization. That is, there is an ambiguity in the definition of u. One can multiply it on the right by elements of the stabilizer group. The action is invariant up to boundary term in this case. So this yeah. U is f, right? So f is equal to u f0 u minus 1, and so u is 1. So we know u is equivalent to uh, where h f0 h minus 1 is equal f0. Okay. So it is written. It's not obvious that it's a function of only u. So here, what one notice here, this is element of the Lie algebra, and so one is legitimate to take the scalar product. These are also element of Lie algebra. One can take commutator and take the scalar product with f. In fact, this is what's called the expression inside the integral. The integrand is called the Kirillov form. Kirillov constant Suryo form. It's the symplectic form on the co-adjoint orbit. Symplectic form, you have to check that this form is independent of the parameterization of u, and also it's closed. So that has been shown. So one can show that it's changed by a total time derivative. It goes to something for small h, it becomes something like, it goes to that plus h dot, roughly speaking. So it does not influence the equation of motion.
What is the, how would you write F, the distribution function in terms of the fundamental Fermi operator?
Distribution function
Yeah.
is not a, well, in the quantum state, yeah. One can try this, the following exercise. We do the Wigner transformation of the distribution function. So I do the following. I take Seidegger x plus s over 2 psi x minus s over 2 integral the s e to I px, and then take expectation value of that over a given state. And if the state is smooth, then it will produce the distribution function. In fact, it's just a Wigner distribution function that approaches the usual distribution function in the smooth, in the long wavelength limit.
Every state that can be obtained by acting with the canonical transformation on the reference state, legitimate Wigner function. Like if you Fourier transform, you get an operator which is a density matrix, positive, semi-definite.
One can construct, let me say, I'm not sure if there is a unique way to do that. If I given a distribution function that is sufficiently smooth in space, one can construct by coherent state formalism a state that that has that expectation value. So the way to do that is to take this, to construct the exponentiate the bifermion operator. So integral over x and y with some function of x and y, Seidegger x psi y. And that function is sufficiently smooth in center of mass. And then act on that the ground state of the Fermi surface, the ground state of the Fermi surface. Yeah, that is varies over length scale much larger than the inverse of the Fermi momentum. One gets a state that has the distribution function that is basically the distribution function of the new state is going to be f0 e to the f e minus f, where this function f is the Fourier transform of this one with respect to the relative coordinate.
When you go beyond the semi-classical limit,
I won't go there.
But every state that you can get this way, it's state that you can get from.
I'm not going that way. I think you are pointing to a.
Functions, you have more functions. You have much more fields than you started with.
No. I have exactly the same number of fields. Well, maybe even less fields than the number of bifermions, Fermi two fermion operator, Seidegger x psi y. Right? Because I'm trying to do a bosonic. I'm trying to make a bosonic description of my theory, so I have to work with bifermion operator, Seidegger x psi y, and there are nothing. Yeah, integral over x is all inside here. Yeah. It's local in x because the so here the scalar product is integral over x of the same point, and now the thing that you have to do is to compute this thing. So let me just show how various terms would appear. So if I compute the u minus 1 dt of u with u equal e to the power of phi, I would get something like phi dot plus phi dot, I think with a factor of 1/2 plus dot dot dot. Okay, so here you start to have derivative over x here, and then more derivatives. So if one work in the in perturbation theory, we will get all terms to be local, but with more and more derivatives in x. It's very unusual because we here it's not doesn't have the form of a field theory in which one can clearly identify the Lagrangian density. So here the group is not a group of internal symmetry. It's a group of some space, not really space, phase space symmetry, and so it's not something that we usually think about. Yeah.
What is U? Like it seems like the specific form of U isn't specified here.
So any distribution function, any state of a Fermi surface is parameterized by a given U, by this formula.
Find this, like, would I say that I have some final distribution function, and based on that, I choose a U to put in the action?
Yeah.
Or
you can use U as a variable in your field theory.
U before doing any calculation, like is U something like e to the Hamiltonian or something like that?
Yes, so U, as I said, is exponents. You can think about as exponent of some function of x and p, and one can fix the gauge, so that is a function of x and the angle on the Fermi surface. Now this function is a field, right? It's not something that you know beforehand. It's a field, and you solve the equation of motion to get this field as a function of time. Yeah.
S was understand. What is S?
What?
S, what is S?
So this is integral over s from 0 to 1. This is a Wess-Zumino Witten form of the action, where the U at the boundary is the physical U, and we interpolate it into the inside.
So identity is given or then U?
Yeah, it's identity inside becomes physical U. Yeah.
If we think about the Fermi surface, so at each angle, I think we have something like a 1+1-dimensional fermion. We can bosonize it, and then we get the bosonic variable for each angle. Is that more or less? I mean, that gives you the same count as degrees of freedom as what you are doing. Is that point of view similar or related in some way to what you are doing?
That is actually what people have done in the past, and we can easily get, say, expanding this action. Let me expand this action to quadratic order. So to quadratic order, we get just a picture that you have said. There is an infinite number of bosons that one can thought of as the result of bosonizing fermion moving in the theta direction. And then the action looks something like phi dot n of theta, so grad phi, and then minus n of theta grad phi squared. Something like that. Here's the bosons. The action depends on the derivative of the boson along the direction of the momentum. Okay, so what one can also. I'm sorry?
Read the first term. First term is first order in time, what we do?
This is phi dot n of theta times grad phi. So n of theta is the vector. So in 2 dimensions, it's just have cosine theta, sine theta components. Yeah. And then derivative, here's derivative with respect to x. And here's another. So if you do that in one dimension, then we have two scalar fields, and you have just a representation of the bosonic action for the scalar in terms of the left and right movers. But here we have infinite number of these movers, one in each direction. To quadratic order, that's the whole story. They are decoupled at this at the quadratic because it's quadratic, so it decoupled. It's actually decoupled even if we include this Landau interaction. So the Landau interaction include a term, would give us a term that is integral over d theta prime times some function of theta and theta prime and theta grad phi at theta and n theta prime grad phi at theta prime. It's non-local in the angular variable, but again, quadratic is the scalar field. So if you expand the Landau, take into account the Landau interaction, we understand why Landau interaction is not really an interaction. There was a very there's a long discussion in Shankar's reviews in Polchinski's Stasi lecture, explaining why Landau interaction is marginal, although looks like a 4-point interaction between the fermions. In the language of the boson, it is part of the kinetic term, just quadratic term. So by definition, that has to be marginal. It's quadratic, completely quadratic. I'm sorry, it's two different theta coupled by a function that is the Landau parameter, theta and theta prime. None. Integrate over xt and theta. X, theta, and theta prime. Yeah.
So here the interactions come from higher order expansions of the very big stuff.
And the Hamiltonian, both.
So can you show that the higher order terms are irrelevant?
Yeah.
Say those
Yeah. So the higher order term looks like this. So let me write the higher order term. So the higher order term looks like, if I expand the Wess-Zumino action, the third order term in the Wess-Zumino action looks like integral dt dx, d theta. Let me write this gradient n and phi. There's two terms, I think. I think I have it somewhere. Down. Let me write it down and then define the notation. So here, gradient phi, that's something that we've seen before. S of phi is S of theta gradient of phi. That is the derivative, but in the tangent direction. S is the direction tangent to the Fermi surface, and n is the direction along the momentum. And theta is derivative over theta. So that is one term that we get by expanding the Wess-Zumino term. You see that it's cubic. The coupling constant, and there is something that comes from the Hamiltonian as well. But by counting here, you see the rule is the following. So in Fermi liquid theory, theta count as 1. space and time count the same way. So this is dimension d minus 1, d plus 1, minus d plus 1. D is a number of spatial dimension. The dimension of theta is now has to be d minus 1 over 2. And you can check that this coefficient, the coupling constant in front, has dimension, the dimension of this operator. The dimension of the coupling constant is like minus d plus 1, d minus 1 over 2. No, d plus 1 over 2. Highly irrelevant operator. So then that's how one can explain that Fermi liquid theory is an effective theory in the sense that only quadratic term is important. Is phi so I'm not completely sure I understand the answer to this question. The total number of particles is quantized, but we don't have the quantization of the number of particles per along each of the direction theta. So yeah. In one dimension.
Any number of dimensions. The way he described it is that you have a 1 plus 1 dimensional field theory along theta, along n theta. We bosonize the fermions, and phi is the bosonized fermion.
But when I say that I bosonize along each direction of theta, actually it means that we have to break the circle into small interval in angle. And it's actually not clear what is the width. So depending on the width of this angle, we would come up with different compactification radius of the scalar. So when we are in more than one dimension, I think I don't have the answer to your question.
Plus 1 dimension.
Yeah.
Where all these intervals are the sum of the two ends of the Fermi surface. Is phi circle value or not?
In this case, I think one can make an argument that phi is circle value. Well, in order to see that phi circle value, we have to put the system, so the way that one can, I think the way one should see the radius of phi is to put a system on a finite space. And then one thing I don't remember where, we have to also compactify the momentum space. I think I can't reproduce the argument, but I think once I convince myself that by doing so, one can show that phi has to be circle value. Yeah. It is the subtle things in this argument that I'm not completely sure about is that I have to make I thought I have to make momentum periodic, but I'm not completely sure. I actually don't remember whether that is necessary.
Dimension 1.
I'm sorry?
Theta, dimension 1.
Why theta is dimension 1. So in Fermi liquid theory, we can zoom in. Basically, it's a choice. If we are looking at the correlation function where a momentum of external probe, where momentum and frequency scale in the same way, omega over Q is of order 1, and then then we can convince ourselves that the whole Fermi surface contribute to such correlation function. We have to then regard d theta as something of order 1. So it is a particular regime that we are looking here. Omega and Q scale in the same way. Theta scale is 1. In this is the cleanest Fermi liquid regime. We can, yeah.
In Shankar-Polchinski RG way of thinking, you just scale the momentum towards the Fermi surface, right? And theta doesn't seem to scale in that RG scheme.
Well, here the thing, the comparison is not really straightforward, because here we are working with this bosonic variable. It's bosonic variable, and it's in principle, it's, yeah, one has to do the counting again. Okay, so let me then mention to you what, so we have talked about co-adjoint orbit, the Fermi liquid theory, the 3-point vertex, and then one can use this to compute correlation function. In particular, we can use the 3-point vertex to compute 3-point function, and 3-point function turn out to match with the result of the loop calculation. So the loop calculation is pretty difficult. We have to take 2 diagrams and sum them up because the direction of the ordering of these vertices can change. We see that in the low omega, low Q limit, there is a cancellation between these 2 diagrams to leading order. The final result is the one that matches with, after cancellation, matches with the result from the bosonic theory. When the bosonic theory gives rise to the final result without any cancellation. Let me also mention one thing, maybe at the end, that one can extend this formalism to a system with spin. Helium-3 have particle with spin 1/2, or electron gas, particle with spin 1/2. And so what one can do to accommodate spin is to extend the notion of the Poisson bracket. So now the generators of canonical prime transformations are functions that can carry a spin index. There is a sector of the algebra that consists of spin singlet operators, and there is also spin triplet operators. I can go from 1, 2 to 3, and there is a non-trivial commutation relation between spin triplet operators, so J, X, and Y, P. In addition to the usual term, one also get the epsilon I, J, K, just the usual F, J, J, K, without any derivatives. And one can check that this is a consistent extension of the algebra of canonical transformation. And one can redo the calculation and find out that in this case, the 3-point vertex is still I'd say irrelevant, but much less irrelevant than it is in the spinless case. So the dimension of the coupling constant, so there is one coupling constant that looks like epsilon ijk, grad n of phi I, phi j dot, phi k. That has the coupling constant with dimension in dimension d equal 2 plus 1. This coupling constant has dimension 1/2. dimension -1/2. And so the loop, the loop contribution that comes out from iterating this vertex is down only by 1 power of momentum compared to the leading order result, rather than 2 power of momentum. So this matches very well with, we haven't checked that quantitatively, but it matches with what people find, that the spin susceptibility of 2 + 1 dimensional Fermi gas, Fermi liquid, has a linear in Q correction at small q. Okay, so let me stop here, and if there's any question.
A very nice series of lectures. We have time for a couple of questions. Yeah. Excuse me.
Thank you for a great lecture. I was just wondering, is there an abstraction to generalizing this formalism for finite temperature?
Abstraction.
So could you generalize to finite temperature, and then the F0 would just be like Fermi distribution, let's say, finite temperature?
One can try to do that. In the, I would be more, I would be more confident with taking this theory as the starting point, and then turn on the temperature in this theory. You can start with the distribution function that is not a sharp distribution function. I think one needs to be at finite temperature. There's the problem that we have to be rigorous. We need to formulate the problem on the Springer-Keldysh contour.
Dissipative effects. You forget about dissipative effects. Just finite temperature, non-dissipative. Then this should work, right? This formula.
It would work, yeah. It works in a way that it just reproduces the usual collision-less Boltzmann equation.
I'm just going to ask if there's. Oh, sorry.
So here in the path integral, you would integrate over all f, right? So the distribution function. So you're parameterizing that integral as starting from some reference state and then integrating over all canonical transformations instead. So, but say if you're interested in a transition where the topology of the Fermi surface changes, is it clear that you can still do that? Because there is no canonical transformation that can tear apart the function.
No, I don't think you can do that. I think then physically what will happen there in this transformation is that you don't have just the Fermi liquid state anymore. It's just not the standard Fermi liquid excitation, but near this singular point, you have some kind of a sector of the theory where you have to single out the degrees of freedom and then couple it to Fermi liquid outside of this point. So that presumably is a harder thing to do.
Can you get a collision term from an action principle?
This action? Yeah, we think about this as the as the theory. Well, this function, this phi, in principle, describe particle hole pairs, and so in principle, I think one should be able to describe collisions with small momentum transfer directly in this formalism. If the momentum transfer in the collision is small, then I think one should be able to do this. So one way to introduce, for example, if the collision is due to the exchange of a soft boson, one need to just couple this fermion, this phi to soft boson, and then that would encode the effect of collision.
Resistivity?
Resistivity of infinite frequency? Frequency, conductivity, in principle, yeah. But we haven't done this. We have to put in the dissipation of momentum in order to get a finite conductivity. We haven't We haven't done that.
Is there something that fixes the overall normalization of the Kirillov form? Like, is it supposed to be integers or?
Yeah. So the Kirillov form doesn't have the coefficient that is fixed by the usual argument that one would use to fix the Berry phase term in the case of a spin. And the reason is that the co-adjoint, well, there the co-adjoint orbit is finite, has a finite volume and has an argument. However, one can show it's the thing that I didn't mention. This coefficient here cannot be a function of time. So this coefficient is, if one tried to make this coefficient to be a function of time, that wouldn't work, because this time derivative term that one gets by changing the parameterization of u would now not a full derivative anymore. So one can make then a quasi proof of the Latinger theorem. This coefficient is fixed in this way that's like is fixed, is continuous with the coefficient in free fermion theory. In free fermion theory, we know that coefficient kappa has to be 1 to match with the equation of motion. So you can imagine taking our system and change the coupling constant smoothly over time. This coefficient at the end should not be a function of time, should still be 1. Now couple the system to U1 gauge field, we can show that the volume of the Fermi surface is equal, volume of the Fermi volume is equal to the number of particles. Yeah.
So far, have you studied this theory only classically or also quantum mechanically?
So far we have done the following. We show that the classical theory reproduces the one loop graph in the fermionic theory. We also can see the following effect, that if we do in one plus one dimension, and for example, start with the fermion with quadratic dispersion relation, then one can show that we need the fermion loop to reproduce correlation function of density near the light cone. So in 1 plus 1 dimension, if the dispersion relation is not straight, the 2-point function has a complicated light cone structure that one can only that we think that it's related to the loop, to now bosonic loop graph in the theory.
Theory as it stands, forgetting that it came from fermions and all. Have you studied anything about the quantum version of this theory, or have you so far studied only its classical theory?
Started thinking but we have not finished thinking about this theory at the classical level. So I think we just started and not.
You have terms like the quantization of the coefficient is seen only in the quantum theory. In the classical theory, the quantization of the coefficient doesn't appear. In fact, in general, in classical field theory, the overall normalization of the action doesn't mean anything.
Sure. Yeah.
All that matters is the equations of motion.
Yeah. We think that
as long as you discuss only the classical theory, I don't see why the coefficient is important, or why there is any discussion about the coefficient.
Yeah, the only discussion is the following. The discussions that I just told you is similar to this discussion. Say if you have a quantum Hall state, and then changing the parameter of the Lagrangian cannot change the coefficient, the level, because if you make this level a function of space and time, the action is no longer gauge invariant. At least you can see that already at the classical level, and so it says that the whole conductivity cannot be changed by a smooth deformation of the system, but it doesn't make you can in the classical theory give an argument that is integer. So the version of the argument supporting the Latinger theorem that I show is a classical argument that's based on the continuity between free fermion and the fermionic interaction.
So isolated Fermi points, if we impose some global symmetry, then there could be anomalies. So that obstruct to gap the Fermi points by preserving global symmetry. In the case of a Fermi surface, have you considered maybe impose some global symmetry and asking whether your theory can capture some anomalies associated with Fermi surface? For example, there could be obstruction to gap the Fermi surface by preserving certain symmetry. Do you think there could be something your theory can help to understand?
It is actually, we think that there is no, how would I say, there's no obstruction in the nonlinear theory to gauge to introduce a gauge field that couple, well, to gauge the canonical transformation. Actually, one can gauge the full canonical transformation, but and we get, it's a nonlinear, it's a non-abelian group. So we get some non-abelian equations of conservation of current. But if we then linearize around the Fermi surface, then we get an equation that looks like, because there are nonlinear terms in the conservation law, we see an equation that looks like an anomaly. Yeah, so this anomaly appears as a result of expanding the theory near a certain state. Yeah.
One last question. How did you find this Berry's phase term?
How
did you find the Berry's phase term that gives you the
Berry phase term?
historical question?
Oh, the historical question. I think we just I forget. Yeah, the result. No, but I think what happened is my collaborator found it. So that's for sure. I didn't. Yeah.
Okay, so let's thank